Hello students, I am Dr. Sadhana, Assistant Professor of Physics, St.Joseph College of Arts and Science, Cuddalore. In the last video, we have discussed about the perturbation theory. In this video, we are going to discuss about the perturbation theory in non-degenerate case. Non-degenerate system is a system which has only one eigenfunction corresponding to each eigenvalue. That is, it has same number of states and same number of energy levels. So in the stationary system, the Hamiltonian H does not depend upon time because it is stable, and it is possible to expand H in terms of lambda as some parameter, and we can have the expression as H is equal to H naught plus lambda H dash plus lambda square H double dash. Now, reducing the lambda is equal to 0, it becomes H naught psi naught minus E naught psi naught is equal to 0, which is the expression for the unperturbed Hamiltonian. Now, it can be directly solved by solving the psi naught naught, psi 1 naught, psi 2 naught, etc. up to psi k naught, and the eigenvalues, corresponding eigenvalues can also be found using the solution E naught naught, E1 naught, E2 naught and Ek naught. So for solving this eigenvalue and eigenfunctions, let us consider the orthonormal set. We know the condition for orthonormality is integral psi star I psi j d tau is equal to 0 if the given function is orthogonal, and it is equal to 1 if the given function is normalized. So it can be represented by the Kronecker delta symbol. So it is equal to 0 when I is not equal to j and is equal to 1 for I equal to j. It means that the probability of finding a particle in a system is possible when it is normalized, and it is not possible if the system is infinite, then it is said to be orthogonal. For a perturbed system, it may be written as psi k is equal to psi k naught plus lambda psi k dash plus lambda square psi k double dash, etc. and Ek is equal to Ek naught plus lambda Ek dash plus lambda square Ek double dash. So if the perturbation is very small compared to the eigenfunctions and eigenvalues, then the terms will become very smaller and the series will be convergent. Now substituting the values of eigenvalue, eigenfunction and Hamiltonian in the general Hamiltonian equation, it becomes H psi is equal to E psi. Here H naught plus lambda H dash plus lambda square H double dash into psi k naught plus lambda psi k dash plus lambda square psi k double dash is equal to E psi. E is a Ek naught plus lambda Ek dash plus lambda square Ek double dash, etc. and again psi. So now simplifying, that is rearranging this equation and collecting the coefficients of powers of lambda, we can have the solution for each and every Hamiltonian, that is perturbed and unperturbed, first order perturbed Hamiltonian and second order perturbed Hamiltonian, and etc. After expansion and reordering the Hamiltonian and energy functions, energy eigenvalues according to the coefficient of lambda, and after that separating the coefficients of lambda, that is lambda for 0, lambda for 1, lambda for 2, 3, etc. It may be written as for lambda for 0, it becomes H naught minus Ek naught psi k naught is equal to 0. And likewise, for lambda, it becomes, for the coefficient of lambda, it becomes H naught psi k dash plus H dash psi k naught minus Ek naught psi k dash minus Ek dash psi k naught is equal to 0. So from this, again rearranging this with the psi k naught and psi k dash, it becomes H naught minus Ek naught psi k dash plus H dash minus Ek dash into psi k naught is equal to 0. So which provides the total Hamiltonian equation for the first order perturbed equation. Similarly, we can rearrange the coefficients of lambda square in terms of H naught and H and E, and rearranging the equation with psi k powers of psi k. So it becomes H naught minus Ek naught into psi k naught is equal to 0 for the unperturbed Hamiltonian, and H naught minus Ek naught psi k dash plus H dash minus Ek dash psi k naught is equal to 0 for first order perturbed equation. And again second order. For second order, we should neglect the higher order terms of lambda square and H naught double dash. So it becomes H naught minus Ek naught psi k double dash plus H dash minus Ek dash psi k dash minus Ek double dash psi k naught is equal to 0. So likewise, it repeats for the third order Hamiltonian equation. By solving these equations to find the energy eigenvalue and the energy eigenfunction, we can find the approximate value to be added with the exact solution of a time independent equation, perturbation equation in a non-degenerate case. Thank you so much.